object database. A number of people here use that. A lot of other people here know about it. If you want to know more about it, ask me. But today I'm going to be talking about threading. Threads and threading in general is a very large topic. And I'm only going to talk today, since I only have half an hour, about some small corners of this topic that I have run into in my work, and some things that I've had to do as a result of the specifics of my work that you probably shouldn't do, and why not. So first there's the term, right? In Smalltalk, a thread is known by the term process. There's the class process. This is basically a change in terminology since the 1970s when Smalltalk was originally designed to now, right? So what was called a process then is now, because of the shared state, a thread. I will try to use the term thread most of the time. I may say process accidentally occasionally. So the real feature of a thread versus a process in today's terminology is that threads share state with each other. And sharing state is the hard part of concurrency. Some languages isolate the state between the concurrently running execution by default. For instance, the E language keeps everything. It's object-oriented, but it keeps, you can't share objects between the threads of execution there. Some languages, by default, share all the state. C shares all the state, Java shares all the state, and so does Smalltalk. And this creates a lot of opportunities for making things happen that you don't want to happen. It's very, very difficult to get this right. And so you normally want to limit the sharing through very, very careful design. In general, shared state threading is a very terrible model, and you shouldn't use it unless you have to. But sometimes you have to, and I have to. The reason I have to is this product called GenBuilder for Smalltalk. And this is also known as GBS. It's a special purpose distributed object system, and it hooks up VisualWorks and VA clients to a Gemstone server with ways to pass objects back and forth and replicate their state and to send messages back and forth and that sort of thing. This product was first released in 1986. I've been working on it since 1996. I've been the team lead for this product since 2002. And GBS uses threads internally, but it also allows an application which is using threads arbitrarily to use GBS. So it's a framework that supports arbitrarily threaded applications, which makes it even more difficult to know really what's going on. So I have to be very careful to not let user programs run into problems with the internals of GBS. So I have to be really defensive. And today, all the examples are going to be from VisualWorks. So inside of GBS, we have these mapping dictionaries. Their purpose is to map identity from client objects to server objects and server objects to client objects, because we have two object spaces separated in two different VMs. And so you look up an object in one, and these structures must be shared between threads. So I'm going to talk about those a bit. One of those is the client map, which is keyed by the client object and its value for each client object. It's sort of an identity dictionary. As it says here, we have up to, in normal usage, you might have up to 2 million keys in this dictionary. You might, under some circumstances, fairly typically be doing about 100,000 updates a second, and you might be doing some hundreds of thousands of lookups per second, maybe as many as 1 million lookups a second. So the structure of this thing, The key is a client object, and it's weak. We map that weakly because we don't want to keep the client objects from being garbage collected. In fact, the client object being garbage collected is usually what triggers removal from this dictionary. It's very seldom that we explicitly remove something from this dictionary. The value is a delegate object, which is mapped strongly. This delegate object contains information about what session that object belongs to, what its identity is in the server, whether or not the state is currently synchronized or needs to be synchronized, that sort of thing. This is going to be, I'm going to talk specifically about the structure in 32-bit VisualWorks. 64-bit VisualWorks has a slightly different structure. So in 32-bit VisualWorks, we have the problem that we only have 16,000 identity hash values. So in 64-bit, there's 20 bits, so we could have 1 million different hash values. And for 2 million objects, that's enough to do a fairly good job. In 32-bit, then we have a lot of collisions. If we have 2 million objects in there and there's only 16,000 different unique hash values, then you have quite a few objects that have the same hash value. So the structure that I use for that is that we have exactly 16,383 hash buckets. And there's an array pre-allocated to that size. And then you just look up and you know which bucket it's in by its identity hash. In VisualWorks, there is never a hash value, identity hash value of 0. So this works as just directly mapping into there. And then once you get inside of a bucket, we have the bucket itself has index instance variables that are the values, which are strong. And then there's an instance variable, named instance variable of the keys that is a weak array. And this key goes with this value, and this key goes with this value, and so on. And the free slots make up a linked list. So you always can find a free slot fairly quickly. So given this kind of structure and the fact that access must be multi-threaded, how do you share this thing safely? Well, we might think of a few ways of doing that. So we have a semaphore, and that's the main synchronization primitive in Smalltalk. And semaphore, back when Smalltalk was being designed in the 1970s, the semaphore was the hot new synchronization primitive. It was like the greatest thing we'd ever seen, and there were older synchronization primitives that couldn't do as much, and so it's very natural that that was implemented in Smalltalk. But I have to look at performance a little bit of that. And I'm going to digress a bit into talking about performance. Here's a quote from Donald Knuth, who wrote The Art of Computer Programming. Premature optimization is the root of all evil. I rather like this. I don't know if it's really the root of all evil, but it certainly is the root of a lot of evil. So really, what you need to optimize for generally are simplicity and clarity in your code. If it runs fast enough, then that's good. Make it as simple and clear as you can, because that's, for these systems that have long life, the maintainability is everything. So, but like threads, I also have to pay attention to performance. And why do I have to do that? I have some customers with tight time requirements. One customer in particular had a system where they had to get a request in on their network, and then they needed to be sending a response out to that request completed in 20 milliseconds. And this was their business. I mean, there was big money on this. And the part of that 20 milliseconds that was allocated to the part of the code that I was dealing with in GBS was 5 milliseconds. So we had to transfer this object graph from the server to the client within 5 milliseconds. And that was working. and then they switched from the 32-bit gemstone product to the 64-bit gemstone product. So now object identifiers, which are part of the data that we're transferring, have gone from 32 bits to 64 bits. So we're sending almost twice the data. So they tested this, and they came up with 9 milliseconds, and this was not acceptable to them. So I went to the customer site, spent a few weeks there, and optimized this, and measured and optimized, and measured and optimized, and got down to 3 milliseconds, which they were very happy with. And of course, you know what happens next. Well, now the benchmark is 3 milliseconds, and 4 milliseconds is unacceptable, right? So, which is good, but we were pretty happy with that. So I have to pay attention to things like this. So now we have to ask, well, what's the performance of a semaphore? Is it slow? Is it fast? Well, let's test and see. So the first thing when we test, right, we take a loop and we say, well, let's run something 1,000,000 times. And the first thing you have to do this with is the empty block, because you're going to be testing the performance of a block. So it's good to know how much an empty block takes. And the answer is, on the machine I ran this on, when I was preparing this talk, is it takes 3 or 4 nanoseconds to execute each time through an empty block. And now all of my tests are going to be run using this same 1,000,000 times repeat sort of thing. So I'm just going to make the results look on the slide like this. Empty block, 3 to 4 nanoseconds. So how much time does it take to run an empty critical block? And the answer is, it takes about 70 nanoseconds. So that's considerably larger than the 3 to 4 nanoseconds overhead for the test itself, so I'm going to ignore that. But is 70 nanoseconds fast, or is it slow?
But is it only once,
No.
It's
It's a million, at 1,000,000 times, it's 70 nanoseconds each. Okay. Each. Yes. Right. Yeah. Each. So is 70 nanoseconds a lot? Well, we don't know. So it's all relative. Well, let's compare that to what it takes to do a lookup. So in order to do a lookup in this dictionary, this is the message you send. So this is the block I'm going to test. How fast is that? Well, that's 40 nanoseconds. So clearly, I'm not using a semaphore, or it would be more than 70 nanoseconds. So what if I do use a semaphore? Okay, so now I've wrapped it in a semaphore critical and test that. So how long does that take? Okay, well, that takes 130 nanoseconds. So that's more than 3 times as long. And there's 20 nanoseconds that came from I have no idea where, but there is. So the question is now, is 130 nanoseconds too slow for this application? And the answer is, well, if I'm doing 1,000 lookups a second, 130 nanoseconds is fine. There's a very small percentage of the time. But I'm doing maybe up to 1,000,000 lookups per second, and then 130 nanoseconds per lookup starts having enough to start worrying about. So maybe that is too slow. So if I was only looking at up 100,000 or 1,000 times per second, trying to get anything better than this would be premature optimization. But since I'm looking it up 1,000,000 times, maybe that justifies doing something else. So what do I actually do? Well, for modifying this collection, I use batched semaphores. I take a whole bunch of these modifications at once, grab the semaphore once, do a bunch of modifications, then release the semaphore. That way I amortize the time, that 70 nanoseconds, over many operations. And for looking it up, which is the most frequent operation, I don't use a semaphore at all. Now, to make semaphore-free lookup safe, we have to do things very carefully. Because we have to give a sane answer even if the collection changes while we're in the middle of a lookup, because our lookup might be interrupted by another process that modifies that collection while we're in the middle of the lookup. So we need to be prepared for anything. So this is the way we do the lookup. So first we find, well, we know what the hash bucket is by that direct indexing, right, into the array. And then within the bucket, we do a linear search for the key, which I don't show the code there, but it's actually a VisualWorks primitive. And then we say, well, did we find it? If we didn't find it, it's just we return nil. If we did find it, then we look up the value. And then we look up the key again and say, is it the same key as it was when I started? And if so, then we're good. And if not, then we didn't find it. Now, why is that safe? It's not entirely obvious why that's safe in just with this. We'll show a little more in a minute. But basically, what we're saying is, I find the key, I know it's there, I find the value that goes with it, and then is the key still there? And if I am, I'm good, and otherwise not. One of the things about this collection is that we never move keys around within a bucket, right? We use the linked list of free things. So if the key at that index is not the same key, then the key that we found has actually been removed. So it's no longer there, which is why it just answers nil. This does require some extra code over what you would use. These last two lines you wouldn't need to do if you weren't trying to do a lookup that was thread safe. But this code was included in that 40 nanosecond figure I showed you earlier, so it's definitely cheaper than a semaphore. We also have to be a little careful. Given that our lookup looks like that, we have to be careful how we add things. In this case, this is how we add things. We find the place to put things, and then we add the value, and then we add the key. And that's the important part, is we add the value first before we add the key, because when we're looking it up, we look up the key first and then find the value. So the value would better already be there. So that's one of the reasons it works. Another reason it works is because VisualWorks uses green threading. Everything is run in a single operating system thread. And within a single operating system thread, we are guaranteed ordering of memory accesses between threads, which would not be true. So one Smalltalk green thread will always observe changes happening in the order that they happened in the other thread. Whereas if you're in two different operating system threads, that is not necessarily the case unless you use memory barrier instructions. It gets harder. But there's actually a hole in this. Theoretically, there's a way to get the wrong value for the key. So we have to think about, well, what is a correct answer for this and what is an incorrect answer? Because if something is in the middle of being added, or something is in the middle of being removed, or something's in the middle of being changed, any state, any answer, because we're not synchronizing, we're not using semaphores to synchronize, any answer that was correct anywhere around that time is actually a correct answer. The real thing that's an incorrect answer that we want to avoid is mapping a key to a value that it never did have and never will have. That would be an incorrect answer. So there is a way to get an incorrect answer out of this, but it requires explicit delete, which is rare, and it requires a bunch of them. So it requires that you find the key, it's there, and then you get interrupted, and a different thread removes that key, adds a different key that goes into the same slot. You grab its value, and then you get interrupted again, and then you remove that key, and then you add back the key you had originally, and then you look up the key to see if it's there, and then you get the wrong value. I actually protect against that in the 64-bit version of this by keeping a deletion count and retrying if the deletion count has increased while I was looking it up. In this version, for 32-bit, I don't do that. I could do that. I probably won't because I'm a little concerned about performance once the deletion count goes to be a large integer. If you're updating these things at 100,000 times a second, you could theoretically get to 2 to the 29th and overflow to a large integer in a couple of hours, whereas if you go to 2 to the 61st, then you've got 2 billion times more than several billion hours before you would run into that. So I don't have to worry about that. But let's go back to this add method, because there's something funny here that I want to talk about. And that is, right about here. All right, there's this ensure where I send it to an empty block with a non-empty block. And that's not just me abbreviating the code, that's the actual code. So why would I send ensure to an empty block? And there's a bit of a story behind that. So once I was reworking many of the lower layers of GBS, and the login sequence of GBS really does a lot of things, and it exercises a lot of the code. So when you're changing a lot of things, there were weeks where the login sequence didn't work. You'd get partway through the login sequence, you'd hit a bug, you'd look at it, you'd close the debugger, and then the state of your image would be messed up and you couldn't continue. And it would be very difficult to recover from. And so I decided that this was a bad thing. That really every state, every point in the login sequence should be able to recover if it was terminated by putting in the proper ensure blocks and if curtailed blocks. So I did that. And I wrote a test to test that this worked, and it was a very abusive test. It had one thread logging in and logging out continuously, and it had another thread that just kept killing that thread, sending terminate to it at random intervals. And it would just do this over and over again for like a minute. And what I found was that even after I had everything working, every once in a while, we'd get hung threads that were sitting there waiting on semaphores, and the semaphores never got signaled. And eventually I figured out why. So this is the code for semaphore critical in VisualWorks. We wait, and then once we're signaled, we run the block, and we ensure that once we are given access to the semaphore, then we run the block, and then we ensure whether we're terminated or not that we signal the semaphore when we're done. So this should be foolproof, right? But what was happening was that execution was getting to right here. We had entered the block, but we had not yet executed the signal. And it was at that instant that the terminate was sent to this thread. And it was actually terminating the thread without executing the signal. So after thinking about this for a little while, I determined that I thought that the semantics ought to be that that when you send terminate to a thread, any unwind blocks that are in process should be allowed to finish. And that wasn't happening. So I reported that to SimCom. They did eventually fix it. I don't think it was particularly easy to fix, but they did. And so this is a little test that you can run in your favorite Smalltalk to see whether it has this problem or not. Some do, some don't. Faro passes this test. VW now passes this test. VA, I think, does not pass this test. They know about this. Gemstone does not pass this test, and I reported the bug a few months ago. So you have this question about how do you respond to terminating when you're in a critical section. If you're in the middle of updating some critical data structure like we were with our mapping dictionary, and you get sent terminate from some other thread, then you don't want to leave your data structure in an inconsistent state. So in this method, what I've done is that by putting this ensure with an empty block, because I don't care what happens here, what happens is that once we enter this, once I start changing the state, I can be sure that all of these steps will happen, even if terminate is sent to this process while it's in the middle of all of this. You know, we could be suspended somewhere in the middle of this, and some other processes could run, and those other threads can then send terminate, but this will be allowed to be finished before it's done. So that works, but really, is that the best way to do this? It seems kind of weird. So there's some other ways we might think about doing it. Well, there's a semaphore, and then there's a thing called value uninterruptedly, value unpreemptively. We'll talk about those. So the semaphore, it's our main synchronization primitive, as I mentioned earlier. Can it help us in doing this? And really it can't. Semaphore, properly used, can protect against interference from other threads, but it isn't really designed to protect against termination. And this whole batch of updates that we're doing is already protected by a semaphore, so we're already protected from other threads, but somebody else could send us a terminate, and then we would lose something. Also, there's that 70 nanosecond thing, so it's too slow for our use anyway. Okay, so value uninterruptedly, this would work, and this is actually kind of designed to do this because termination does in VisualWorks interrupt the current thread, and there's, but this is also used by the debugger and things, so using that might possibly affect the debuggability of the code. And also, it uses a semaphore in order to do this, so it takes about 87 nanoseconds. So for the purposes, since we're doing this frequent operation, it's slow. Okay, value unpreemptively, this is kind of the big hammer. This raises the priority of the currently running thread to the maximum so that it can't be interrupted by any other thread until you get done with your block, and then it lowers the priority back down where you were. And this would work, but it does more than I need it to, because I don't really care if another high priority process interrupts my update of this dictionary. In fact, if it's a high priority process, I kind of want it to, because it's presumably high priority because it's important. And as long as I get to finish my thing and make my thing consistent before I go on, I'm okay with that. The other reason not to use it is that it's even slower. So how fast is my empty and sure block trick? How much overhead does that have? Okay, this has about 15 nanoseconds overhead. So that does seem like the right way to do it. So that's a little corner of some of the things that I have to think about when I use threads. There's a lot of things to think about when you use threads. So based on my experience, don't use threads unless you have to. If you do use them, keep the state as separate as you possibly can between the threads, and keep the patterns of sharing state as simple as you possibly can. Avoid the evil of premature optimization. If you're only sharing the state 1,000 times a second, you don't need to do any of the stuff that I did. Do it whatever way is the most straightforward, which is probably semaphores. And if you do have to use the kind of things that I've used here, please comment your code explaining what you're doing and why. I do have comments in my code. If you want to see the full code, talk to me later. Questions?
Hola.
So my question, Martin, is probably naive. So have you considered moving some of the methods of the bucket, the dictionary, the lookup, the add, probably the remove, into the VM side? I don't know if VisualWorks allows you to have custom primitives like you do on Gemstone or BA, so that I imagine reading that at the C level or at the VM level would help in both the performance and the critical section, because if you just call a primitive, you won't get interrupted, like it would be a Smalltalk code. So that is the question. If you consider that, if you see an issue with that possible solution.
That's an interesting question. I haven't seriously considered it. VisualWorks does not let you do custom primitives as such. It would have to be an FFI call. FFI calls in VisualWorks are fairly slow. I don't have a number on that. It would be interesting to find out. As it turns out, because of the things I've done, when you benchmark this, when you profile it, the dictionary operations do come out down in the single digits of the time spent overall, because there's a lot of work in marshalling and unmarshalling these objects to go over the wire and that sort of thing. The dictionary operations are definitely there and they're frequent, but they're down at the 3 to 5% level. So I haven't seriously considered trying to make them any better than they are.
Any other question? Yes.
I have a simple one. Did you refactor the ensure in the empty block to be a selector in the block closure? Just like instead of value uninterruptedly, having something like value ensured and document the behavior there?
You could do that, yes. And if I used it in more than one place, I would want to do that. In fact, I think this is the only. I think I only do that trick in one method, so I just documented it there. But yes, that would be that would add to code clarity. I like that. Thank you.
Okay, so now it's time for a break, and then our first keynote from Giselle.
Yes.